Good evening everyone and welcome to the Q&A session 49 from the playlist of IIT-JEE Main Physics. The topic is the graphical interpretation of the magnetic field inside and outside a current carrying hollow cylinder as shown in this figure. So based on this topic I have one question for this session which is written here on this board, and the question is: a hollow cylinder of inner radius r by 2 and outer radius r carries a current I. So we have to plot the variation in the magnetic field from the center to a point outside the cylinder along the radius. So in this question we will be using the Ampere Circuital law, which says that the line integral of magnetic field is mu naught times the net current which is passing through the area enclosed by the closed surface. So there will be three cases now here. First case, when x is greater than equal to 0 and less than r by 2. Second case will be when x is greater than equal to r by 2 and less than r, or in this will be less than equal to r, and the third case will be when x is greater than r. So in the first case, when the x is greater than equal to 0 and less than r by 2, so in that case if I use the Ampere Circuital law, that is the line integral of the magnetic field around a closed surface, this is equal to mu naught times the net current which is passing through the area enclosed by that closed surface. So here in this case, since I is equal to 0, so in the first case when x is greater than equal to 0 and less than r by 2, so the value of b will be, so in the first case, that is when x is greater than equal to 0 and less than r by 2, so in that case the value of the magnetic field will be equal to 0. Now let us move on to the second case. In the second case, x is greater than equal to r by 2 and less than equal to r. So in the second case, I will be using the Ampere Circuital law again, and this is so if I use this Ampere Circuital law, in the second case I will be getting, now b, this will be equal to line integral b, now dl, here this will be, so in the second case I will be the point x, let us say this is the point P here, which is lying at a distance x from the center. This is the point P here. This is the point P which is lying at a distance x from the center. So in that case this will be equal to b, now this dl, so the area enclosed by the closed surface enclosing this point P, this will be equal to 2 pi x, and this will be equal to mu naught times now I. So this is the net current which is passing through the area enclosed by this closed surface which containing the point P. So now we have to find the value of I in this case. So in order to find the value of I, we will first of all find the cross-sectional area through which this current I is flowing in this hollow cylinder. So the cross-sectional area will be pi r square minus pi r by 2 whole square, which is equal to r square by 4. So this is equal to 3 pi r square by 4. So this is the cross-sectional area through which the current I is flowing. So for this surface area which is enclosing this, so for the closed surface area enclosing this point P which is at a distance x from the center, so the cross-sectional area will be pi x square minus pi r square by 4. Now we have to find the total current which is passing through this cross-sectional area. So corresponding to this cross-sectional area, the current is equal to I. So for this cross-sectional area, the value of I will be, this will be equal to I divided by 3 pi r square upon 4. 3 pi r square upon 4 multiplied by pi x square minus pi r square by 4. So from here the value of B will be equal to mu naught upon 2 pi x. This pi can be taken outside. So finally I will be getting this value as 4I upon 3 r square x square minus r square by 4. So from here we can see that as the value of x is increasing, the value of b will also increase. So for the second case, so now I will be drawing, I will be plotting the variation in the magnetic field now. So this is the x-axis, this is the y-axis. On the x-axis I will be plotting the distance, and the y-axis I will be plotting the value of magnetic field. So this is, let us say this is r by 2, and this I'm just taking this as r. So when x is equal to this r by 2, so when x is equal to r by 2, then in that case the value of b will be equal to 0. So first point here I am getting here is this one. And when x is equal to r, then I will be getting r square minus r square by 4. So let us say the value which I am getting here, let us say this is the value of the magnetic field when x is equal to r. Let us say this is. Now here the magnetic field will be varying in the form of a curve as shown in this figure, and beyond r, that is when the point, let us say it is lying here, there is another point, let us say q, which is lying at a distance x. So in that case what will happen, I will again use the Ampere circuital law. So that will be BDL is equal to mu naught. Now for the point this q, the net current which is passing to the closed surface enclosing this point q will be equal to I, and so this can be written as I, and so B will be equal to mu naught I upon naught 2 pi x. So as the value of x increases, B will be decreasing, the value of B will be decreasing, and when x is tending towards infinity, then the B will be tending towards 0. So something, the curve will be like this, that is when the value of x is very large, then the value of B will be tending towards 0. It will not be 0, but it will be tending towards 0. So the graph will be something like this. So thank you very much for joining this session. Now in the next session I will be continuing with the same chapter, that is the magnetic effect of current. And in the next session I will be coming up with a totally different type of a question. So till then, have a nice day. Bye.